Hello everyone, welcome to Spark Study. In this video, we'll study about the concept of dominant pole. So, what is the dominant pole? What is the effect of the dominant pole, the transfer function, and how to find out the dominant poles from the transfer function, and what is the effect of the stability in the transfer function of that particular system? We'll study about all those things. Okay, let us consider a transfer function. Okay, the transfer function is, let's consider 1 divided by s plus 10 into s plus let's say 1. Okay, s plus 10 into s plus 1. So we know that the auxiliary equation is the denominator of the equations or denominator of the transfer function when equate to 0. So we can write the auxiliary equation is equal to s plus 10 into s plus 1 equal to 0. And from the auxiliary equations, the auxiliary equation becomes 0 if either this is 0 or this is 0. So to make that, if I equate this to 0, I'll find s1 is equal to minus 10, and if I equate this to 0, I'll find s2 is equal to minus 1. So in this case, if I try to plot the S domain, S plane equation or S plane graph, we know that this is my real axis and this is j omega axis or imaginary axis. So with that, if I further extend this to, I'll find one pole over here, that is minus 1, another pole over here, that is minus 10. Clear? This is very clear. So this minus 1 corresponds to 1 by s plus 1, and this minus 10 pole corresponds to 1 divided by s plus 10. So everybody clear about this thing? And if I take the Laplace, inverse Laplace transform, that means this is in s domain or frequency domain. Let me convert this into time domain, so I can write the inverse Laplace transform of these two signal, or these two function. We can write this is e to the power minus 10t, and for this it will be e to the power minus 1t or simply e to the power t. So if I try to plot these two graphs, then it is very clear that this will take more time to die out and this will take very less time to die out. Okay, so you try to take different value of t and try to plot. So this is my t and this is this y-axis corresponds to this equation, then you will get this kind of graph. So from this graph it is very clear that this graph or the pole which create this kind of response is available for time more than this time. That means, let's say this is t2, this is t1, so we can write this as t2 is less than t1. Okay, so let us recall our analysis. We are doing transient analysis. That means we'll study the transient behavior of some or certain system. So that to study the transient behavior, we need to know what is the behavior for certain time. Okay, that is why you are not using the impulse signal, because impulse signal is quickly dying out. So you are using step signal for the response. So if the impulse signal is not using, because when time tends to 0 it die out, that means we need to think about some time gap. Okay, so the more time gap is very useful for transient analysis than that of the very small time gap. Okay, this does not mean that this is a bad system, but this system can be analyze more efficiently in case of transient analysis than the grid system. Clear? That is why we can say this pole is dominating in nature than that of this pole. Okay, so once the first pole or the pole corresponding to 1 by s plus 1 is dominating in nature with these two, this pole, this is called dominant pole, and this pole is called insignificant pole. So the pole which can use for subtransient analysis is called as dominant pole, and the pole which is not actually used for transient or subtransient analysis, that is called insignificant pole. Clear about this? Okay. If we try to make you understand more efficiently, then I can draw a line over here, and let's consider this is my S plane. Try to make it understand, and let's say this is the range where the significant pole occurs. Significant pole or dominant pole location. Clear? That means from this is the S plane, and the right side is completely unstable and left side is stable. Let us consider this region is the pole of significant pole or dominant pole. What about the value? Let's say this pole value or the extreme point value will be x. So that multiply this x by 5 to 10 times, so that we'll reach with this side of region, or from here to here the distance will be 6 zeta omega n. So from the second order equation, you have found zeta, you also found omega n, and multiply this omega n zeta with 6, so that the value we found, this is the value or this value. Or we can say the poles lying here, if that pole is more than 5 to 10 times lying in this region, then this pole is called insignificant pole. And the pole lying in this region is called dominant pole. So we can write this is 5 to 10 times. Clear? So there is no perfect value of this value. Let's say one pole is here minus 5. Okay, so let's say one pole is here is minus 5. If minus 5 is dominant pole, then 5 times or 10 times, 5 times of minus 5 will be minus 25, which is somewhat lying here. This is called insignificant pole. This is dominant pole. Okay, so for transient analysis, that means if the system consists of insignificant pole, then you have to remove that insignificant pole for the transient analysis. That is important. Okay, so to remove, and after removing, so you can say this let's say equation a by b minus c. So if you a by b into c, so if you remove this b, then you have to do some certain adjustment in the equation. Otherwise, how the equation will make an effect? If you remove one term, then that means the system changes, right? So in that case, to change one term, or to remove the insignificant pole, we have to make certain change in the system gain. Okay, so we need to learn about that. So we have some notes. So take the notes first. So the notes will be the horizontal distance from a closed loop pole to the j omega axis, okay, the horizontal distance from the closed loop from a closed loop pole to the j omega axis determine the settling time. Determine the settling time. Settling time. That means the larger will be the distance, the lesser will be the settling time. Okay. Due to that pole or settling time. Okay. So the smaller is the distance, is the longer of settling time. The smaller is the distance, the longer is the settling time. That means if this is my j omega axis, if the pole is here, another pole is here, so the settling time for this pole, so this is the j omega axis, this is the horizontal distance, and for this is the horizontal distance. So this distance is less than that of this. If a system constituted of this pole only, so the horizontal distance from j omega axis is less than that of the other system which constitute this pole whose horizontal distance is more. So that the settling time of this pole is less than that of settling time of this pole, because I told TSS inversely proportional to the horizontal distance from j omega axis. Clear? So the larger will be the distance, the smaller will be the settling time, and the smaller of the distance is the larger of settling time. So that we can say if the poles are lying much far from the j omega axis in the left hand of the S plane, the system is more stable. That means if you give some disturbance to make the system stable or operating in a perfect region, it takes very less time if the system distance or the pole distance is very large. Okay, because whenever you come from here little bit further towards right side, if you reach 0, then the system become marginally stable. It may go out of stable or it may come back to the stable, but a little step towards the RSP or right side of right hand side of the S plane will make the system completely unstable. Okay, so that as far as you go left side towards the S plane, the system stability increases. If you go to a right side of the S plane, the system stability decreases. Remember in the mind, I repeat, if the pole going towards right side of the S plane, the stability decreases. Okay, and it crossed the j omega axis to the right side, then it's unstable. But if the poles approaches towards the left side of the S plane, then the stability increases. I repeat over here, if a pole is here, okay, and it approaches to the right side, so once it approaches the right side, here system is more stable than that of here, than that of here. It is marginally stable. Then when it go right side, it become completely unstable. But if the system pole lying here, it is completely unstable. When it approaches to the left side, its stability increases, and when it crosses the j omega axis, it comes over here, then the system becomes more stable. Clear? This is very important. Remember this thing. So as we study that the poles which is 5 or 10 times lesser than the insignificant pole is called dominant pole. So dominant pole generally comes in pair, that means in complex conjugate form. It doesn't mean that it always comes. It may comes a real part also, but generally it comes with complex conjugate, so that if the system becomes complex conjugate, the response will be like this. Okay, but if the system is only real part, the response will be like this only. Clear? So most often you can see the complex conjugate form of the dominant pole. Okay, so we can say that always most often the dominant poles occur in complex conjugate form, and this dominant pole plays a vital role in the transient system analysis. Remember this thing. Okay, so for eliminating an insignificant pole, I told you earlier that if let's say k by s plus a into s plus b, where a is very larger or 5 to 10 times of larger than that of b, so this is dominant pole, this is insignificant pole. So as my transfer function consists of dominant pole and insignificant pole, so this actually created a difference in the transient analysis. So we need to remove this term. Okay, so if I remove this term, the system remains, the transfer function remain k by s plus b, which is completely different from this transfer function. Clear? So that, remember, we need to remove this insignificant pole, fine, but what happened? We need to make some change to the gain only, because we could not do any change in the other pole, so that we have to change the gain. So we'll study, we'll do some problem how to remove this insignificant pole, and how to do the change in gain. We'll study in this video. So let us consider a problem which states that the second order approximation using dominant pole concept. Okay, what is that? Second order approximation using dominant pole concept. Okay, using dominant pole concept of a given transfer function of the system given. Okay, so the system which is given is nothing but 5 divided by s plus 5 whole into s square plus s plus 1. Okay, so this is the transfer function which is given. So by looking into the transfer function, we can say this is third order. Okay, because this is square term, when multiply with this s, this becomes s to the power 3, so third order. But we need to approximate the system to second order, because we are studying second order systems. So here we need to study, if some system is more than second order, then we can approximate the system to a second order. That means if somehow in some problem or in some exam they have asked what is the value of transient time, like your delay time, what is your rise time, what is your steady state time, what is your peak overshoot for this transfer function, we are blank, because we have studied to find all those things for second order system. We have not studied for third order or more than this order, more than second order. What to do? So we need to approximate those systems. If we find some dominant pole, then the transfer function can be approximate or can be made to second order system. Let's see how to do. The step involved is find out all the poles first. Unless you find out the poles, how could you say that this is dominant and this is insignificant? So first to find out the poles, so from looking these two, so you can make S1 is minus 5, and this is second order quadratic equation. To solve that, let's say, so minus 1 plus minus b square means 1 minus 4 into a into c, so 4 under root divided by 2 into 1, that is 2. So we'll have S2 is equal to minus 1 plus minus under root 3 by 2, and S3 is equal to, not plus minus, only plus, okay, only plus, and equal to minus 1 minus root 3 by 2. So we have two poles here. This extremely sorry, this is minus 3, this is also minus 3, under root of minus 3, this is not 3, it's under root of minus 3. So this under root of minus 3 gives imaginary term. So we let bother about only the real term because we need to find out the horizontal distance. So real term is minus 1 by 2 for here, minus 1 by 2 for here. So this is minus 0.5. You can say this equal minus 0.5. So S1 is minus 5, where S2, real part of S2, and S3 is equal to minus 0.5. So if you compare these two, we can see S1 is equal to 10 times of S2 or S3. So that it is very clear that this S2 and S3 is dominant and S5 is insignificant. Clear? So if you learn this thing, now I can remove. What to do? So I need to take the poles, or I need to make in this form that 1 plus something. Okay. So what to do? You can see here 5 divided by, if I take 5 from here, so 5 whole into S by 5 plus 1. It's clear now, 1 plus something whole into S square plus S plus 1. Now what you to do? We need to remove this thing. What to do? Make S equal to 0 or j omega equal to 0, or make the frequency of this term 0. Clear? Why the frequency of this term 0? Just imagine. I told you, if the poles near to the origin, the transient time is more. If the pole is very far away from the origin, transient time is very less. If transient time is very less, okay, if the transient time is very less, then the frequency of oscillation is very less, or you can say the frequency of oscillation is approaches to 0. Once the frequency of oscillation approaches to 0, so the j omega becomes 0. So that we can remove this S term. Oh, it's not visible. Let me make it clear again here. Okay, so this is 5. So this is 5 divided by, I'm taking common 5, this becomes S by 5 plus 1 into S square plus S plus 1. Okay, so I need to make this to 0 because I told you why I need to make this to 0. So once I make this to 0, 0 by something is equal to 0, plus 1 is 1. So ultimately I remain with 5 divided 5 whole divided by 1 into S square plus S plus 1, and this ultimately becomes 1 divided by S square plus S plus 1. Clear? So the previous term which we have earlier, or we can see that we need to approximate those things, na? The question is given 5 divided by S plus 5 into S square plus S plus 1, and we have approximate this transfer function into 1 divided by S square plus S plus 1. And if I compare, if you try to simulate these two functions, you are getting approximately same response, not exact but approximately same response. But you can see that here when I remove this insignificant pole, so the insignificant pole is not appearing here. Okay, So when I say this, you can see that there is change in gain and the gain changes to 1. Okay. So remember this thing, how to do this kind of problem if someone asks in the competitive examination. Okay. So this is all about the concept of dominant pole. So we will meet with some other concept in the next lecture or next video. So if you like the content, please don't forget to like, share and subscribe to Spark Studies channel. Thank you very much. Thank you very much.